So there are two type of things which you have to do in the problems. One is to express the relationship between dimensional variables as so some of the problems will be only of this type. Express the relationship between dimensional variables as a relationship between different pi numbers. And here what you will find is the number of variables will decrease because each group will be a pi number. And the second thing which would come, which could either be part B of this problem or an independent problem, is where you may have to do scaling and modeling. So let's look at the workbook. Problem 1. If you have the workbook on your devices, you can open that. So this is the first problem. It says there is a model propeller 600 mm in diameter, which is tested in wind tunnel. Air approaches the propeller at 45 meters per second, and you find it rotates at 2000 rpm. The thrust and the torque are measured. Okay. Now, what is thrust? Thrust is a force and torque is a moment. You need these because you need to know the dimensions of these. So thrust and torque are 110 newtons and 10 Newton meters. Sometimes, if you do not even understand these words, the dimensions which are given, for example, it says thrust is 110 newtons. So then even if you don't know what is thrust, you should be able to realize it as something which has units of force. So it must be a force. Of course, there could be a confusion because torque and energy have the same units. But as far as dimensional analysis goes, they will be the same. But physically, of course, there are two different quantities. Now it says it is known that Ft and T, Ft is the thrust, T is the torque, they depend on diameter D by propeller speed. Obviously, it is implied it is the angular speed because, and then air speed V, viscosity mu, and density rho. Okay. Then they say the prototype, always the prototype is the actual or something like the actual of the same size. A prototype 10 times as large is to be built. At a dynamically similar operating point, approach airspeed is equal to 120 meters per second. So then it says calculate speed, thrust and torque of prototype propeller neglecting the speed, the effect of viscosity but including density. Maybe I could have added a part. First, I could have put there, express this as a non-dimensional relation. Okay. So now, here, if we look at, let's say the thrust first, and the torque will follow similar thing. This is a function of diameter, the angular velocity of this thing, the approaching velocity, mu and rho. If it was only this problem, I could have neglected mu. But I'm first forming a number with mu and then, but when you have things like this, neglecting the effect of viscosity, then what you should do is do not include viscosity as a repeating parameter. Because eventually when you simplify in the later parts, then you'll have to neglect viscosity. If you use this, you will have to do your non-dimensionalization again. Okay, so this is what it is. Then when we, so if we now choose we can choose rho v and d or rho omega and d as the repeating variables. Okay. Now, again, let's try to, in terms of if our variables are the ones which we know, then we don't have to do this exercise of ft times rho to the power of a, omega to the power of b, d to the power of c is equal to m0, m0, t0. You can directly from here. So now let's form the pi groups. Pi 1 will be equal to force. Now with, if I'm using rho Vd, what should I use to non-dimensionalize? Once again, keep in mind, rho V square is pressure multiplied by area. So therefore, if I'm using rho Vd, it will become rho V square d square. If suppose I'm using rho omega d, then also keep in mind omega times d is velocity. So therefore, then what you will do is rho v square is omega square d square times another. So just do things like this to make life simple. So either this will be pi 1 or this will be pi 1. Then secondly, we have used rho, V and D here. So we have to now form a pi group with omega, because that is the omega and mu. These are the two. Totally, if I count 1, 2, 3, there are 6 variables. And we have chosen 3 repeating variables because there are 3 basic dimensions. I did not even do step 2, which was to check how many basic dimensions are there, because it is obvious. In certain problems, mass may not be there. If it is only flow rate and kinematic variables, then mass will not be there. Then you have to use only 2 repeating variables. Okay. So now what will be pi 2? How do I make a pi group with omega? So now here, if I'm using this set, it will be omega. I know omega d has dimensions of velocity. So omega d by v will be pi 2. If I'm using this set, then I will have v by omega d. Because now v has to be non-dimensionalized in terms of omega. And the third variable has to be formed with mu. So now whenever mu comes, either you do it m by LD or you remember Reynolds number. What is Reynolds number? Rho Vd upon mu. So therefore mu divided by rho Vd. And if I'm using this set, then it will be mu divided by rho Vd will be omega d square. So I can directly do this by inspection. It is only if you come across some new variables, like I give you a problem in heat transfer, etc., where you have to use temperature also as a basic variable. So then you can in your mind combine things and see that you get a non-dimensional variable. And you can do it by inspection. There is no need to follow the formal method. But formal method will always work. So this is what we have. So the non-dimensional relationship is Ft divided by rho v square d square is some function of omega d by mu and mu by rho vd. And in this case, what we will get is Ft divided by rho omega square d4 is a function of v by omega d and mu by rho omega d square. Both are equally acceptable. Okay. Now, in the problem, what does it say? Firstly, it says effect of viscosity is negligible. So now, if viscosity is negligible, and that is one reason we did not use mu as a repeating variable. Had we used mu as a repeating variable, it would have come on the left hand side and it could have come on the right hand side. Okay, so because mu is not important, so we can directly write Ft upon rho v square d square is some function of omega d by v. And if I'm using this one, I will get Ft upon rho omega square d4 is equal to some function of v by omega d. Now the condition for similarity will be condition is omega d by v for the prototype is equal to omega d by v for the model. So using this, because we know omega d and v for the model and we know d and v for the prototype, we will get omega p. And keep in mind, D prototype by D model is 10. That is what is given to you. Even though you don't know the actual values of D, but the ratio is given, and that is enough. Okay? So you get omega p. Now you say, because omega D by V is same for model and prototype, then Ft divided by rho V square D square of the model is equal to Ft divided by rho V square D square for the prototype. And once again, Ft for the model, rho V square D square for the model are given. If rho is not given, probably both, if both are here, then rho is the same. In some cases, and then mu is of course not a factor here. So from here now, you can work out the value of Ft. Okay. So omega you got, Ft you got. Similarly, what you can do is for thrust, you build up, thrust will be nothing but force multiplied by one more length. So therefore for torque, sorry, not for thrust, torque. So for torque, the non-dimensional number will be rho V square D cube. Okay. So this again for the model and you can easily get the torque for them. So these are, see, while doing the problem is very straightforward, but the concept and the simplicity it leads to basically is coming from this functional relationship. That the torque and the thrust are only functions of omega d by v. So if you match omega d by v for the model and the prototype, you can estimate the thrust force on the prototype if you know the thrust on the. So while calculations are very simple, but overall the concept is very, very powerful. That you carry out tests on something which is geometrically and similar to the actual situation, then you are able to estimate the forces or the quantities which you need on the huge prototype, which otherwise would be very difficult. Okay, so that's why this dimensional analysis is quite straightforward. So other problems, I'm sure you should be able to do them. What I thought was, in the remaining time, let me maybe take up some other problems and some more concepts rather than. I'll do what you want. Do you want me to do more problems on this or to cover? One thing I wanted to do was to tell you at least the third problem of the quiz, because many of you gave it for regrading and actually you missed out something. So maybe I will do that. Okay. I'll put out the solution also. So let us look at the sixth quiz, which talked of it said that there was a container like this in which fluid of density rho 1 And similarly, density rho 2 enters through 2 with velocity V2, area A2, and the gauge pressure there was equal to P2, and fluid of constant density, and this was also constant. In the chamber, they get mixed thoroughly and exit to atmosphere with density rho 3 and velocity V3. Area is equal to A3. Okay. Now, the first part of the problem was to find rho 3 and V3. Both of them had to be found separately. Okay. So now here, obviously, most of you did it correctly, at least the half of it was done correct. Most of you applied the mass balance, and mass balance gave us rho 1 V1 A1 plus rho 2 V2 A2 is equal to rho 3 V3. But this was only half the story, because this will only give you rho 3 times V3. It will not give you rho 3 and V3 separately. So the second equation which had to be used here was volume continuity. And volume continuity gives us dV by dt is equal to okay. Now, because both the fluids are of constant density, the left hand side is 0. There is no change in material volume of each particle. So, left hand side was 0 because each fluid has constant density. So, even when they mix, the particle volumes don't change. And we choose a control volume. So, I should have done this before. I choose a control volume This is my control volume. Yeah. Rho 1 is different, rho 2 is different. But individual particles, their density is not changing. Okay. Now this control volume which I have chosen is fixed. So this term also becomes 0 because CV is of fixed volume. So what this gives me is V1A1 plus V2A2 is equal to V3A3. And you could have also got this by doing some sort of a mass balance, that whatever mass this, if you think of trying to calculate the density of the mixture which is going out as the sum of the two masses divided by the volume, you would also get the same result. So therefore, these two equations had to be used. And from here, now you can get rho 3 as well as V3. Now, some of you have used, I had given 8 marks for this. If you had used only one of the equations without bothering about other, I have cut 5 marks. I have given only 3. If you have tried to find rho 3 using either Bernoulli's or something else, maybe I've given 1 more mark. But full 8 marks have been given only if you have used these 2 equations. Okay? So that is why some people have returned the quiz. I have written no change because they did not know the right answer. So that's why I'm specifying. Okay. Now the next part of this was to find the force on the support. And what was given to you is that the connections at 1 and 2 are flexible and do not apply, or no force is applied by the fluid on those connections, or those connections do not apply any force on the fluid. That means they will get pulled or pushed and they don't offer any force. So now on this control volume, let's have a look. This is our control volume and this is the cut. So obviously what is going to happen is the cut is going to apply a force, let's say Rx and Ry, on the control. Now also it was given, see, when I look at the overall control volume, I can divide the pressure forces as gauge pressures plus atmospheric. And atmospheric pressure all around will cancel out. So that means only gauge pressures remain. And P1 was the gauge pressure which was given in the problem. So P1A1 will act at 1. And similarly, P2A2 will act at 2. On 3, there is exit to the atmosphere, which is like a jet. So therefore, the pressure is atmospheric. So there will be no pressure. So the total external forces which are there are these. And then also we have weight plus rho 3 times volume of the fluid times G. These are the external forces acting on the control. Okay? Is that clear? Then what do? You take your equation that sum of forces is equal to okay, this is your force equation. Now, one mistake a lot of you have made is have combined all the forces, treated it like a scalar equation. Obviously, this is a vector equation, so we have to write the x component and the y component separately. Lot of people have written P1A1 minus P2A2 is equal to minus rho V1 square A1 plus rho 2 V2 square A2 minus rho 3 V3 square A3 and etc. etc. So that is wrong. You have to separate it out in x and y components. You can't treat it like a scalar equation. So let us write the x equation first. And when we write these equations, let's be very clear. Let's write things, just focus on one term at a time. So when I write sigma, sum of forces in the x direction, so left hand side will only consist of what my free body diagram tells me. So what my free body diagram tells me is sum of forces in the x direction is P1A1 and then I have Rx. Now some of you, and very wisely what they have done is, instead of calling it Rx and Ry, they have written it as minus Rx and minus Ry, which are the force on the support directly. This Rx and Ry is the force on the control volume. So force on the support will be minus Rx and minus R. Some of you have directly written as minus Rx, which is perfect, if you understand this. Okay? I am treating Rx and Ry as force on the control volume. So these Rx and Ry, these are forces on the CV. Anything else in the x direction? Nothing else. Now, this d by dt term, there is mixing going on, but we assume that it is at the same rate and everything. It's a fixed control volume. So this d by dt term is assumed to be 0. Of course, you may say there is mixing, so at each point there must be something changing with time, but whatever is happening has sort of smoothened out, so with time things are not changing. And it is a fixed control. So this term becomes 0. Now this term has to be calculated only on the surfaces. So now in the x equation, this will become Vx rho v dot n dA. And if velocities are all uniform, this integral has no meaning, it will just become a product. So now when I look at this first term, here area 1, that is where the flow Vx is non-zero. What is Vx there? V1. So this first term will become V1 times minus rho V1A. Why does the minus sign comes? Because the flow is coming in. At 2, there is no Vx. Rho V dot n is not 0. But at 2, there is no Vx, so this term at 2 will not contribute to Fx. Okay? And at 3, what do we have? We have the same thing, V3. Now we have rho 3 V3A. That's it. So now a lot of you have missed out P1. And I have taken out 2 marks for each pressure being missed. So some of you have returned the copy saying, I have done it correctly, but if you have missed out P1, marks have been deducted and not about at least 2 marks for each P. Okay, is this clear? Now in the y direction, we have minus P2A2. I'm assuming x and y like this. Then we have minus W minus rho 3 Vg plus Ry. So these are the only, see for the force part, go to the free body diagram. Don't bother about the flow at all. Just look at the external forces. So this is what is on the left hand side. Okay. Now on the right hand side, again we have V rho V dot n dA. Now for the y direction, there is only one contribution at 2. And this is where a lot of you have made mistakes. So this will be equal to, now let's see, V2 is equal to minus V2 because it is in the minus y direction. And then we have rho 2 V2 A2, but this also comes with a minus sign. Why? Because flow is coming in. So overall, this term has a positive sign. And this mistake has been made by many people. They have written this as minus. Okay? And this I told you, so you have to be clear. And then once you get this, then you will, from here, you will get Rx and Ry in terms of the given variables. And then final step comes force on the support is equal to minus Rxi minus R. Yeah. हाँ हाँ उसका केवल ये था कि उन सपोर्ट्स के कारण, that means, see, otherwise if I'm cutting at these supports, there will be some force which will come. By saying that, I just said that there is no force coming from the from the two inlets. But if you have specified and not considered rho V1 but still written something, I have given you some credit. I have not given zero. If you have at least written that because it's flexible, we don't count anything. But obviously, I then cannot give you full marks, but some credit has been given if you have thought of that and written that. So in all these problems, you should, if you're making any assumptions, please write them, because they help in case if you have made a mistake. If you've done it correctly, then it's okay. Normally, we have to grade so many copies, so we don't ask you to specifically write the assumptions, but. And then there was a part which was just for 2 points. If Bernoulli's equation can be used. Well, obviously, we cannot use Bernoulli because it's difficult. You can't find a streamline because things are mixing inside. So there could be any reason you could give. You could give their mixing losses. You could say difficult to find a streamline. You could say density is changing because you have fluid coming in from one. At the exit, the density. When we are using exact solutions, of course, you should expect problems from this. We have spent a lot of time. Of course, I did not give you any homework which was graded, but I gave you enough problems. 5 or 6 problems are there in the homework sheet. 2 or 3 problems are there in the workbook. Solutions of all of those have been given to you. Okay. Now here, see what happens is that you have basically these are our Navier-Stokes. Now what you will find is in most problems, rho times A, the whole of the left hand side is 0, except in the spinning cylinder problem, what you will get is maybe there may be more terms depending on the problem, but in the spinning cylinder problem, where there is fluid in the cylinder or in a concentric annulus and the cylinder is spinning, so there you get partial P by partial R is equal to rho V theta square. And this should not be surprising. Why should it not be surprising? Because if you have a spinning body, then even if it is spinning at a constant omega, the acceleration of particles is not 0. Acceleration is rho omega square R square if it was a rigid body, isn't it? And that is what is being shown here. Rho V theta square upon R is nothing but rho omega square R square if it was a rigid body. So physically also you try to see, but in all the other problems, for example, we looked at flow down an incline. Even there, acceleration was 0. Even though there was a flow down the incline, the particle velocities were not increasing as they went down the incline. It was a fully developed flow. And so, there are certain terms which become 0 in the Navier-Stokes equations. So, certain velocity components are 0 in the exact solution. So these components these component equations generally are integrated to give the pressure distribution. In most of these, many of the problems, the pressure distribution comes from these components and it may not come out fully. You may get it as P is equal to something plus a function of Z or a function of R or a function of theta. Okay. So the zero component, the velocity is zero. Those components have a big role because they will give you the form of the pressure distribution. And from this, what you will do is, you will take partial P by partial, this is the non-zero velocity direction. This is determined from above. So some idea of how the pressure changes with the velocity in the non-zero direction comes from the relation above and, most important, the boundary conditions. Those two things you will use to get the variation of pressure in the direction where the velocity is not zero. And why do you need that? You need this term for the Navier-Stokes equation for the velocity in the non-zero. And this term, so it may be a bit vague, but this term is needed. They follow from continuity equation. So the guideline here firstly, simplify the dependence of all variables as specified in the problem. And for this, you will need conditions like steady, fully developed, sometimes some things may directly be given. It may be given in the problem partial P by partial Z is 0. So then just use that. So first thing you have to do is simplify the dependence of all variables. Okay. And then, in fact, actually there is a step, I will call it A1. A0 is the boundary conditions. Even before you solve the problem, state and write all the boundary conditions because they will be needed finally. And to state the boundary conditions, you do not need the solution of the equation. You just need to understand what is physically going on in the problem. If there is a spinning wall, then V theta is equal to omega times R at that wall. If there is a liquid air or a water air interface, then shear stress is 0. Convert it to velocity. Okay? So and then if there is a fixed wall or a solid wall, then the velocity of the wall is equal to velocity of. I think these are the three major. And another thing is, if there is the gas interface, then pressure is constant over there, unless if it is given. You may come across a condition where a hydrostatic pressure distribution is there on the boundary. So then use the hydrostatic pressure distribution on the boundary. So all those things could be there. Okay. You simplify the dependence. Then the next step is we should first go to the continuity equation. And continuity equation typically will simplify one component of the velocity. Either it will become 0 or it will be constant or function of only one variable. For example, if you come across a situation where partial Vx by partial x is 0, it's given to you, then continuity equation for 2D will become partial Vy by partial y is equal to 0. So Vy will become constant. Now if there is a porous wall, then you know at the wall Vy will be equal to velocity at the pore. And if it is constant, that means Vy is the same everywhere. So it did not be 0, it may become constant. So whatever it is, this will give you one very big simplification. Okay? Other simplifications might come in axisymmetric flow, velocities will not depend on theta. If there is no gravity in the theta direction, pressure will also not depend on theta. So things, steady flow, if it is unsteady, then you can't say partial by partial t is 0. Then that will stay. And then you go to the Navier-Stokes equations. And my recommendation is, first go to the simplified component of velocity. The one which you have got. Now, here, of course, you will also have to use the boundary condition. In continuity equation also, you will need to use the boundary condition. And then you go to the simplify. You can do it the other way also, but then you'll have to leave the problem midway and get some inferences from this component. So the best thing is to get to the simplified component, and generally this will give information about pressure. Why? Why does this give you information about pressure? Because velocity is already known. Of course, there are many more terms. Sometimes things may not exactly split, but this will generally give you the information about pressure. And keep in mind that pressure, you always have partial P by partial X, partial P by partial R, or partial P by partial Y. It is not a total derivative. So this is what this equation is going to give you. And when you integrate, this will give you P is equal to something, P is equal to some known function, plus now this constant will be a function of the other variable. It will not be a constant. These are partial equations. And once again, either boundary condition on pressure will give you the full solution for pressure, or you will get some information. So, and then you may have to use boundary condition for pressure here. And then move to the Navier-Stokes equations for velocity component which is not known. Okay? And now you have all these informations, and here then you will have to integrate and use boundary conditions to get full solution. Now the full solution will be that of velocity. So Now, this may not be the final answer. The problem may ask you to find forces, or it may ask you to find flow rates, etc. So once you have the velocity profile, then this velocity profile, use this to get shear stresses, get VNP and flow rate if asked. And you may also be asked to integrate stresses to find force. And these integrate means integrating on the surface of the solid body which is there. And that will give you the forces and moments. Now, what I've told you here is actually, I have told this to you for with respect to exact solutions. But even in the most complex problem, this is the same methodology we will use. But what we will do is, here of course in the class, we are using the Navier-Stokes and solving exact solutions. In real life, exact solutions will not be available. So we will go to the computer and we will solve these equations on the computer. And this branch, as I told you, is called CFD. We use CFD to solve these equations, and then again, as an input to the CFD, the boundary conditions have to be specified, because all the solutions will depend on boundary conditions. Different boundary conditions will give you different solutions. And once you obtain the velocity profile, then on the surface of the body, you will integrate the pressure and the shear stress to get forces and moments. So now, let's say if there is flow past a wing or something. By doing the CFD, you will be able to get the pressure distribution and velocity distribution. You integrate, that will give you the forces on the wing. Now, what may happen is, you may treat the wing like a rigid support. So, because of this flow, there will be forces on the wing. And if this is a solid body, what will it do to the wing? It will cause deformation. So the wing may bend, and this bending, how will you calculate? Using what we have done in solid. That if a particular force is acting, if there's a bending force, then that causes a deflection, and that deflection. So this is how you will be combining solids and fluids. So the deflection on the wing will be calculated by calculating the forces using fluid mechanics, and then the deflection will be calculated using solid mechanics. Okay? Now this was an easier problem. We have insects which are flying, birds which are flying. So this may be a rigid wing. So let me write this down. Calculate forces due to flow using pressure and stress and integrating on the surface. Now deflection of the wing Okay. Now this sort of This problem may be more complicated if the wing is flexible. Actually, birds and all, when they fly, the wings are flexible. That means it doesn't bend like a rigid body. So there then you have to do a coupling of the equations of solids and fluids to be able to get the full solution. So if it's a flexible wing, then we have to do a coupling of equations of solids and fluids. And that coupling, you have to do it maybe an iterative way. This force causes a bit of deflection. Then using that, calculate the new deflection, and you keep on doing it till you reach an equilibrium stage. So this is how then things move on, and you calculate like this. Yeah. Okay. हर चीज एग्जाम में क्यों देखें हम? कुछ चीजों को तो हमें देखना चाहिए ना. हाउ But if I give you the formula for deflection, and if I give you, if you are asked to calculate what is the force which is coming on somebody, I think deflection तो निकाल ही सकते हो. Flexible करो या नहीं करो. So anyway, we'll see what to do. I think at this note, I think this is the right time to say an end to this course. We have sort of tried to summarize. I've tried to summarize. आप तो end के बाद आ रहे हो. हमने तो course खत्म कर दिया. So anyway, so we have seen basically in the whole course, if you look at it, we studied equations of solids, equations for fluids, and I think I have been able to bring out to you what is the difference in a similar situation. For example, if a torque is applied on a circular cylinder, which is solid, and if I apply torque, we have done this problem on a fluid body, how the two are different. Hopefully you have been able to appreciate this. We have done the governing equations both for solids and fluids. And our major focus, in fluids we did a lot of differential analysis also, but major focus was on integral type of analysis where we integrated the equations and found the solutions. We did not do differential form for solid mechanics. We did only integral form of torsion, bending, and different problems. But that's all. And well, it was a pleasure teaching you. I enjoyed teaching the class, and I hope you also enjoyed taking the course with me. Thank you.